This is a field that I've sort of been on the edge of for a long time. One of the papers that Steve and I wrote was about using pulsars to detect backgrounds of gravitational waves. But we'll come to the point where I talk about the work that my thesis advisor did in this, which is fairly central and is one of the things that kind of has shaped what I want to talk about in this talk. So I'm going to talk about gravitational radiation. I'm going to do a little bit of a historical tour of how we got here, where the ideas that go into Einstein's theories of relativity come from, which I think helps give a sense of, you know, why this isn't all just science fiction. And on where we go from here and kind of why at least astronomers think this is interesting. And it's not sort of the gee whiz, Einstein is right. I mean, that's kind of interesting, but at least most of us in the pulsar world were convinced that Einstein was right and gravitational waves were real 20 or 30 years ago. And so that piece of it is less interesting in a way than what it has the potential to tell us about the universe. And that's central in some ways to the idea, as we'll see, that this is a gravitational wave observatory and not just a detector. So I think probably most people were aware of this announcement about a year and a half ago that gravitational waves had been detected. This is from the announcement paper, and the instrument that did it is called LIGO, the Laser Interferometry Gravitational Wave Observatory. It has two detectors, one in Hanford, Washington, and one in Livingston, Louisiana. And what it saw are, and I'll get to how the detector works in a minute, jostling of very sensitive mirrors in a long laser interferometer. And the key thing about the detection was that virtually the same signal was seen in Hanford as was seen in Livingston, Louisiana. So what you're seeing is a wave that passes from one detector to another 3,000 miles away and produces just the same sort of jostling in these mirrors in one as in the other. And that's what confirms that it's not just some random jostling. And the chirp, can people hear the chirp? Yeah. The idea behind that is that the signal, the jostling gets faster as the wave progresses, or what you're seeing is first a slow jostle when the binary that produced it was moving relatively slowly. And then it gets faster as the binary spirals in and then crashes. These are colliding black holes. And the audio is basically taking the signal that jostled the mirrors and saying, well, if instead of jostling a mirror in a long vacuum chamber, it had jostled air molecules and produced a sound wave, this is what it would sound like. So what you're hearing is the fact that the frequency of the wave speeds up as the system spirals into its final collapse. So what scientists have deduced this signal were two black holes, one about 36 times the mass of the sun, one about 29 times the mass of the sun, spiraling together, getting so close that they go inside each other's Schwarzschild radius, collide and collapse, and produce in the end a black hole of about 62 solar masses. And then what you see, if you do the math there, is that means that about 3 times the mass of the sun disappeared, and where it disappeared was into gravitational wave energy. So the waves that we're seeing come from the transformation of the mass of the two black holes into gravitational wave energy, which then spreads out across the universe and eventually gets to us. This source and the other ones that have been seen since, the two more detections, are on the order of billions of light years away from us. So it's been traveling out across, billions of light years of universe for billions of years before getting to us. So this is an enormous amount of energy, and we're just seeing a really, really faint signal from it.
Did you observe a ripple in space? If the space between you and me stretched or compressed, we wouldn't notice it if we had made marks on our metaphorical rubber sheet, for example, using equally spaced rocks, because these marks would also get stretched further apart. But there is one ruler that doesn't get stretched, one made using the speed of light. If the space between 2 points gets stretched, then light will take longer to go from one point to the other. And if the space gets squeezed, light takes less time to cross the 2 points. This is where the Ligo experiment comes in. It has 4-kilometer-long tunnels and uses lasers to measure the changes in the distance between the ends of the tunnels. When a gravitational wave comes through, it stretches space in one direction and squeezes space in the other direction. By measuring the interference of the lasers as they bounce between the different points, physicists can measure very precisely whether the space in between has stretched or compressed. And the precision needed is incredible. To detect a gravitational wave, you need to be able to tell when something changes in length by a few parts in 10 to the 23. It's like being able to tell that a stick 1 sextillion meters has shrunk by 5 million.
That was a clip from a longer movie, but I like the stretching and shrinking of space. So a little closer up view of what's going on with the interferometer. The idea is that you have a laser, you have 2 mirrors. The laser sends light down the 2 paths, and that gets reflected back and joined up again. And if you adjust things exactly right, you can arrange it so that if the path length is equal, the laser light adds out of phase, so you have peaks and troughs in the waves. If you align things just right, a peak and a trough will cancel, so you can send light down both arms of the interferometer and have it come back and produce no light at your detector. And the way these instruments are set up, that's kind of the default state. If nothing is going on, your detector should see no light. But if one of these gravitational waves comes by and does this stretching one direction, shrinking the other direction, the light travel times will be slightly different, and so the waves won't line up exactly right when they come back, and you will get a signal in the detector. And so that's what's being looked for. This kind of makes it sound simple, but as we'll see, it's not. It's a major engineering task. But before we get to that, just a few more cartoons. This is the picture of what a gravitational wave would do to space. This one is looking at a circle of dots, which if there wasn't a gravitational wave would just be a circle. Gravitational wave passes through it, shrinks it in one direction, stretches it in another, and if you thought of kind of a mesh tube of these dots, what the gravitational wave would do is shown in these cartoons. So you're looking for a very subtle shrinking and stretching of the distance between points. And the way that this is generally measured is called the strain. And what it represents is the shift, the sort of fractional shift. So a strain of 10 to the 21, 10 to the minus 21, which is what detectors like this are generally looking for. That's kind of the sensitivity you need to get something that's likely to be able to observe waves that are reaching the Earth. Means a change of 10 to the minus 21 or 10 to the minus 21 meters per meter. And so 10 to the minus 21, 10 to the minus 10 would be 1/10 billionth. and then, so this is 1/10 billionth of 1/10 billionth. So one of the things you don't want to do is try and do this when you only have a meter of wavelength. So one of the things that you need to do to build an instrument that has any hope of being able to see waves that produce this level of strain is make them large, because the larger you can build them, the greater the, when you add up the 10 to the minus 21 in each meter, you get something that you could hope to detect. So these are the two detectors in Hanford and Livingston are built with 4-kilometer long arms. So this is one arm. It's 4 kilometers long, and it's a 4-kilometer long vacuum tube. These are not actually the largest vacuum chambers in the world. That honor goes to the Large Hadron Collider, but they're next. So you pump all the air out down to a vacuum of 10 to the minus 12 atmospheres, so that's at least in the level that people can still come up with numbers for them. That's 1/trillionth of an atmosphere. And the reason you do this, well, there are two reasons. One is that if you had air in the vacuum chamber, it would scatter the laser light, and you want to get as much light down the 4-kilometer length as you can. But even more important, if you have air molecules in the arm of the interferometer, the air molecules would hit the mirrors, and air molecules are moving. They carry a certain amount of momentum, and every time an air molecule hits something, it jostles it a little bit. And we don't notice this very much, but if you're trying to measure something where you're looking for an accuracy of 1 part in a billion billionth, you do notice when air molecules hit mirrors. So the reason that you need to pump all the air out is to simply to stop air molecules jostling the mirrors at the end of the interferometer more than the gravitational wave that you're looking for will. So you have 4-kilometer long arms. The light path looks something like this. So laser, it looks, way simple. Laser, beam splitter to split the light into two halves, sends it down to a mirror. The mirror reflects it back. These are all, this is over 4 kilometers. There's a certain amount of engineering that goes into trying to maximize the light you get, but that's beyond the scope of this talk. And then in the end, it combines into the photo detector. Another little cartoon of this. So light bouncing back. As you change the relative lengths of the path, the amount of light you get at your detector changes. And this is showing what's going on with the waves and troughs, or the peaks and troughs of the light wave. So when the arms are the same length, they add out of phase, and you actually get no signal. And then if you stretch one of the arms, you start getting a light signal. So what the detector is measuring is the amount of light that comes and how that changes with time. And then the final bit with the kind of the engineering piece of this is what one of the mirrors at the end of the arm of the detector looks like. It's a fairly, what you want to be able to do is isolate it as much as possible from all the other sources of jostling, like trucks going by. You can even this is in central Washington. The waves hitting the shore 100 miles away are detectable if you're not if you don't work really hard at isolating this. And the way that's done is by a succession of pendula. So what this does is it basically isolates it from what else is going on around it. The swing of the pendulum will proceed relatively independently of what's happening to the point that the pendulum is hung from. A way that, the most familiar place you see this is in the big pendula that they have in science museums. I don't know if OMSI has one, but the Foucault pendulum, which was used to demonstrate that the Earth rotated. You have this big pendulum that swings back and forth, and as the Earth rotates, it swings back. It's staying in the same plane in space, and the Earth is turning under it. And the way they usually do it, I should have made a slide of this, is to have it knock over dominoes as the Earth turns, so that you have the pendulum swinging in a constant direction in space, and the Earth turning under it. And it's the same principle here. So you have, in this detector, 4 stages of suspension to isolate the mirror at the bottom. And so what you want in order to be able to detect the gravitational waves you're looking for is that the masses at the ends of each arm, and I mean the people working on this call the mirrors test masses, because the idea is they're masses that the gravitational wave is coming and jostling, and kind of mirrors just on happenstance. You need them to be stable to less than 10 to the minus 12 meters. So you need them to be able to hang in space and stay where they are at a level of, and then again, this is just talkable about 1/1,000,000,000th of a meter. So isolated from vibrations from air molecules, and that's the level of stability that they achieve in these detectors. And obviously this was not an easy task. It's actually, there was an interview with somebody who was working on it and talking about how this was exciting, and sort of, they'd never believed that gravitational waves would be detected so soon. And the person pointed out that, well, actually, they'd been working on this for nearly 50 years. So the first thinking about how you would do this started in the late 60s and early 70s. The idea that the best way to do it would be with a laser interferometer was fairly generally accepted by the early 80s, and there was some design put forward. The really serious work on it started in the early 90s. It turned out getting it going was as much a management challenge as anything else, that the people who had the really clever ideas and the passion behind it were mostly theorists working on general relativity. They're not people who, in previous background, work on big engineering projects that involve building vacuum tubes 4 kilometers long. So figuring out how to meld their expertise with the expertise of people who know how to get large projects going was really in the early 90s, and this was when I was at Caltech. This was something you kind of wondered, are they going to get this off the ground? But they got funding from the NSF in 1992. They built kind of a first stage of it, a 1 kilometer interferometer, with the expectation that this would probably only see something if it was a really, really big signal, but that they would get most of the infrastructure they needed in place and iron out a lot of the engineering kinks. And then the second stage was built in the, starting a little over 10 years ago, and completed actually just before that. The detection that was made came in one of the very early operational runs of the upgraded system. So it was, you know, after 10 years of having a system where you were hoping to see something, you turn on the new one and kind of, you know, everybody's reaction was wow. And in fact, one of the reasons it took as long as it did for them to make the announcement, and you know, the announcement was made in February of 2016, the actual event took place in September of 2015, was making sure that there wasn't something odd happening in the system. And the first reaction of a lot of people working on the project was, oh, somebody put in a test signal and didn't document it properly. And so, you know, what we've seen is a test that somebody made. And so they basically had to go back through all the fingerprints that a test signal would leave and check that they weren't there before they were ready to say that they had actually seen a gravitational wave event. So this September 2015 was one of the first operational run, and almost immediately they got a signal, and they've had 2 more since then. And just kind of where this is in terms of what people are interested in gravitational waves. This LIGO was the first generation, so in principle the first generation could have seen the signal that was seen by the upgraded version. The current system is advanced LIGO, though it's not quite at the capabilities that it will eventually be at. And what this sees is relatively fast types of gravitational waves, the last stages of in-spiraling binary systems. And as I'll get to, these were one of the most obviously potentially detectable signals, and they are in fact what has been seen. There are other systems that can potentially see more exotic systems, much more massive binary systems. So, you know, it sounds like 60 times the mass of the sun is really massive, but potentially, you know, we know that there are black holes that are 1 million solar masses or more in the centers of galaxies, and events that involve those are going to progress more slowly, not on the time scale of seconds, but on the time scales of minutes, days. And you need longer detectors to be able to see those. And that's just because the Schwarzschild, the event horizon of the black holes is larger. And so, you know, they end up as a much bigger object, so you get lower frequency gravitational waves from them. And then one of the things that people are interested in, kind of, you know, cosmologically, is signals from the early universe. Those are going to have been stretched out over the billion years that, 13 billion years since the Big Bang, and you're going to be seeing very slow ripples in very slow stretching and shrinking of space. And those, probably the best way of detecting them is not going to be with anything on Earth, or even in the LISA that's talked about here, which I'll talk about right at the end, is, you know, moving the interferometer in space. This is actually using radio pulsars as clocks that will measure these, and so there you have detectors that are thousands of light years away and can conceivably be able to see the fluctuations that are left over from the Big Bang. But that's kind of speculative at this point. So that's kind of an overview of the system. And what I want to kind of point out for the why it's interesting question is to remember that virtually everything we currently know about the universe has been brought to us by light, or more broadly speaking, electromagnetic radiation. That we've gotten, we've sent a couple of spacecraft to planets and picked up samples. We've brought moon rocks back, but that's really close to home. If you go outside our solar system, everything we know about it, aside from a few cosmic rays and a few neutrinos that just happen to land on Earth, has come because we get electromagnetic radiation from the object, and we're able to make sense of it. And it's not just that we get electromagnetic radiation from the object, we get it that it's traveled to us pretty much unimpeded from where it originated. So if we see a galaxy and we say it's 5 billion light years away, there is a photon, a light wave, that's been traveling to us for 5 billion years without running into anything else. Maybe a few have been picked off by interstellar gas and we can see that they're missing, but we can see that galaxy because a wave of light has made it across the universe to us, to our telescope, to the CCD camera on the back of the telescope nowadays, and we can look at that light and make some sense of it. So this is how everything we know about the universe is obtained. And kind of the history, and this is where I'm going to do the brief tour of how we got here. What I want to kind of combine is both a look at how our ability to capture light has expanded over the last few centuries, and how that has given us the insights that led Einstein to come up with the theory of relativity, which has led to the detectors. And then in kind of the second half of the talk, where this is kind of hitting a wall in terms of what we're able to understand about the universe and why gravitational waves are interesting. And the punchline, which is basically it's an entirely new way we have of gaining information about the universe. So these are produced by objects that don't produce electromagnetic radiation, that they're waves that don't interact with matter the same way that electromagnetic radiation does. So basically it's a whole new way we have of looking at the universe. So, brief tour, and I think this is going to be very brief. So this is kind of a mad dash through the last 500 years. I'll start with Kepler. Most people start with Galileo, but I have a fondness for Kepler. He and Tycho Brahe were the kind of the last, the crowning achievement, as I say here, of naked eye astronomy. So Kepler came up with laws of motion for the planets. His key insight was that they move in ellipses, and he did that all with observations that were made without a telescope. So basically just looking at planets, their points of light in the sky, figuring out where they are, figuring out how they move, doing lots of pencil and paper calculations, and working out that they move in ellipses and that there are relationships between the size of the orbit and the speed of the orbit. And these are still basically in use today. Newton explained where they came from, but when we look at the pictures of orbits of binary systems with neutron stars and black holes, what people talk about is adding Einstein's relativity are post-Keplerian corrections. So that what Kepler was able to do with the naked eye observations has been able to explain almost everything about what we see in terms of the motion of objects in the universe up until the corrections that were needed from Einstein. So, whoops. This was Kepler's view of the universe. It had, 5 planets, the sun, the moon. He didn't even know about Jupiter's moon. There were stars out there. All you really knew about them was that they were distant. he provided lots of circumstantial evidence that the planets orbited the sun, but at this point you couldn't prove that. There was nothing that he could do with his observations that could tell you unambiguously that the planets orbited the sun. That insight, or what you needed to really get there, came a few years later with Galileo's observation with a telescope. So again, here you expand what you're able to see, and in this case it's just gathering more light, larger magnifications, and you get a different picture of the universe. So you start seeing that there are mountains on the moon. He discovered the moons of Jupiter. The phases of Venus is a neglected insight. That was one of the real key pieces of information that told you that the planets orbited the sun. And that was, that's something that you could not explain in any other way. And he was also the first person to begin to think about the ideas that ended up being incorporated into relativity. He wanted to argue, he was trying to convince people that the Earth was moving, and so he wanted to convince people that the Earth could be moving and you wouldn't notice this. And he made the argument that has persisted in physics, that if you're moving in a smoothly moving ship, there's no experiment that you could do that would tell you that it was moving smoothly rather than sitting still. And you can, nowadays it's almost easier to understand that, thinking about sitting in an airplane. As long as there's no turbulence, you can kind of go on with your daily life in a cramped seat without noticing that, it's not like you open the luggage rack and things go flying forward or backwards. Things behave pretty much like you'd expect them to behave until things start getting bumpy. And this is the idea of what that gets incorporated, is called Galilean relativity. That if you're moving in something that's at a constant speed, that it's not accelerating or turning, there's no experiment that you can do that will tell you that it's moving rather than stationary. The other argument he made was that all objects fall at the same rate. The story is that he dropped objects off the Leaning Tower of Pisa. It's not clear whether he did, but
4. Cameras on. 2.
This
1.
Experiment.
Release.
This is in a vacuum chamber for a BBC documentary, dropping a ball and a feather. And they do, in fact, fall at the same rate. And this, in many ways, is the key thing that Einstein took seriously that led him to general relativity. As we will see very shortly, Newton explained kind of on a coincidence type level why this is true. But Einstein said, this is telling us something really fundamental about the nature of space and the universe. So the basic relativity principle is that you can't tell whether you're in a moving frame of reference, as relativistics like to talk about it, or not. You can't do any experiments that would tell you that, and you don't need different physics books. You don't need, a copy of a physics book that's, used when you're moving at high speeds. Newton comes along, and he pulls a lot of this together into a kind of unified mathematical framework. They published in Principia both Galileo's ideas about motion, inertia, objects in motion tend to remain in motion, and explanations of gravity. And basically, he mathematically formulated Galileo's idea about inertia into his laws of motion, that you need a force in order to change something's motion. His theory of gravity explained why objects fall at the same rate. Basically, you have a force of gravity that depends on the object's mass. You have how easy it is to move an object depends inversely on the object's mass, and so kind of they cancel out. And this explained, you can take Newton's laws of motion and you can derive all of Kepler's laws. It's a little messy, but you know that, and you can get everything that Kepler figured out from these tedious hand calculations of observations. You can calculate from Newton's laws of motion. And the great victory, you know, in terms of convincing people, just like Einstein had to convince people that relativity was right, Newton had to convince people that his view of gravity was right. And the big victories were predicting the behavior of comets, Halley's Comet, the behavior of the planet Uranus that was discovered by Herschel in the late 1700s. Its final vindication, in a way, came with the discovery of Neptune, where after Uranus was discovered, and this is made for it seemed to be moving a little faster than you'd expect, and then 20 years later, and I didn't get this moving quite at the right speed, you could see it slow down a little bit, and a mathematician, Vernier, worked out that if you put a planet where Neptune is, that would explain what was going on. And a couple of groups went out and looked at it, looked for it, and found it. And so this was, Newton, 200 years later, Newton really was correct, or 150 years later. The only little chink in this is that there were some irregularities in Mercury's orbit that you couldn't explain. Mercury's orbit is fairly elliptical, and it was doing things that couldn't quite. People looked for planets near it and couldn't find it. So this is what the universe looked like around 1800. It was still kind of mostly the solar system. People had started mapping out stars, but they were still very distant. There were these fuzzy blobs that most people were interested in, maybe because they might be comets, but then they found out they weren't comets, and so the Messier, the guy who put together the first catalog of nebulae, basically put it together so that comet hunters wouldn't bother spending time on these. So these were these kind of fuzzy blobs, and nobody was really sure what they were. So my first bit of bad prognostication, I like bad prognostication, was in 1835, the philosopher Auguste Comte sort of surveyed the understanding of the universe and said, well, there's lots of stuff we know, but we'll never know anything about kind of what stars are. We'll never know what they're made of. We'll never know how hot they are. This is just something fundamentally unknowable, as he termed it. But unbeknownst to him, people were starting to look more closely at what light really was and what it could tell us. So ultraviolet light was discovered in around 1800, as was infrared radiation. At that point, there wasn't really much you could do about it, except it was a beginning of an understanding that there was radiation coming to us that we couldn't actually see. So there might be something more out there. Even more interesting, people were starting to use spectrographs to break the light out into its colors, and notice that in the sun there are dark lines that nobody could really explain what they were. And this became a great tool for astronomy, and remains a great tool for astronomy. It's what tells us an awful lot about both what things are made of and how they're moving. And just one of the things to kind of remember is that up until the mid-1800s, all of even telescope observations were done by looking through them, that recording what you saw was something that's really only about 150 years old. But back in the laboratory, this is what gave lie to Compt's prediction. Chemists were realizing that you could identify chemical elements by what sort of light they gave off, and then realizing that the lines in the sun matched with those, and that what this was really telling you was what the sun was made of. And in fact, the element helium was discovered first in the sun because there was a line that chemists couldn't explain, and then later discovered on Earth. And for the relativity question, the most interesting thing that was going on is lots of experiments in electricity and magnetism. And these were all put together into kind of doing to electricity what Newton had done for mechanics by James Clerk Maxwell in 1873. The treatise, I'm told, is impenetrable. And fortunately, it can all be summarized as 4 equations, so that's all that modern physics students have to know. And the 2 interesting things for what we're looking at is that it predicted that jiggling around electric charges would produce waves that propagated through space at a speed that was remarkably close to the speed of light. And the other, so that's telling us that there's more to light than we can see. The other thing that was really curious and bothered people a lot was that this speed of wave propagation comes up in his equations. So it's a constant that's in his equations. And so this is a problem for Galilean pictures of relativity, because this is sort of suggesting that there's some rest reference frame out there that you should be able to find, and maybe physics really is different in moving frames from rest frames. Another bit of bad prognostication. So Hertz discovered radiation. He went out and said, Maxwell's theory predicts that I should be able to get low frequency electromagnetic radiation. He produced them in the lab. One student, as students tend to, asked him, well, what good is this? And he said, oh, no, it just, cool experiment shows Maxwell was right, no possible good use, practical use at all. So, but from our point of view, the big conundrum was that this speed of light in the equations. And it was kind of assumed that this meant that there was something out there, some medium that light waves traveled through. It was called the luminiferous ether. And that if you did a careful experiment, you ought to be able to detect how the Earth was moving through. Because, you have the Earth moving around the sun, moving through space. You should be able to see things, figure out how the Earth is moving with respect to this. And with an experiment very reminiscent of the Ligo experiment, but 100 plus years earlier and without lasers, Michelson and Morley set out to measure how the speed of the light travel time changed as the Earth moved through the ether. The analog is a swimmer swimming against and with the current, and the swimmer going across the river will take less time than the swimmer going up and back, first against the current and with the current. And so they expected to see the same effect of the light travel times being different because of the different speeds of light through the ether, and they didn't. So they found absolutely no evidence of the ether, absolutely no evidence that the speed of light was ever any different, no matter how you looked at it. And then a bit of bad prognostication in the other direction. We can't know, it's like we do know. So here's this person who's just done this experiment that gives him a result that nobody can really explain, but he is still happy to say that basically we understand everything about physics, and it's just finding the last few decimal points of numbers now. So that was 1899. Einstein had been thinking about this question for about 5 years. And what he did was said, okay, I'm going to take really seriously this idea that the speed of light is constant, that Maxwell's equations work in any reference frame, and I'm going to see where that takes me. And that took him to special relativity. It took him 10 years to figure it out. It's actually, once you buy into the assumptions, which is that physics looks the same in all smoothly moving reference frames, and that one of the ways that physics looks the same is that Maxwell's equations work and the speed of light looks like the speed of light, 300,000 kilometers a second. The algebra actually falls out fairly quickly. It's something you can derive many of the results with high school algebra. So he comes up with this theory of special relativity, and it works really well for explaining electromagnetic effects. It kind of unifies electricity and magnetism, but it works really badly for gravity. So he can explain why you don't need different electromagnetism textbooks in different reference frames, but he can't explain why you don't need different gravity textbooks. And that was what then led him to spend another 10 years coming up with general relativity. So I will zip very quickly through the special relativity ideas. Basically, the idea is, and this is something that is deeply counterintuitive because we all live slow-paced lives compared to the speed of light, is that no matter how you're looking at light, you're going to observe it moving at 300,000 kilometers a second. So, if I shine a light beam, I see it moving at 300,000 kilometers a second, and somebody who's moving past me at nearly the speed of light will look at that same light beam and say it's moving at 300,000 kilometers a second with respect to her. These were all stolen from a textbook where the person in the spaceship is always named Jackie. You can find the textbook, Google special relativity Jackie, and you come up with the images. So I will skip over the details of special relativity space-time. So then what Einstein did with gravity is say, okay, I'm going to take Galileo's observation really seriously and say it isn't just some numerical coincidence that mass as it comes into the gravitational force equation and mass as it comes into the how hard is it to move an object equation happen to be just the same thing. I'm going to say this is fundamental, that I'm going to extend this idea that the universe looks the same in all smoothly moving reference frames to all frames that are in what's called free fall and a gravitational field. And that's also kind of counterintuitive, but spacecraft vomit comets that get you weightless. So as long as it's free falling, everybody's weightless. It's like they're in empty space. It's not that there's no gravity there. It's that because the people and the orange Nerf balls or whatever they are, ping pong balls, I guess, and the spacecraft or the airplane are all moving in free fall. And this is what the plane that does that is doing. So there's this moment where it just falls as gravity is pulling it, and that's where everybody feels weightless. And what Einstein's fundamental insight was that's what, I'm going to build my theory of gravity around the idea that you cannot tell that it's any difference between being in that airplane in free fall near the Earth, so falling in the Earth's gravitational field, that experience of 0G is just like the experience of being far, far away from any gravitational source at all and being weightless. There's no way you can tell. So he adds this idea that there's no way to distinguish between just sitting still in empty space and falling in a gravitational field. So, you know, you can picture that you're sitting in empty space, far away from anything, being weightless. Physics is simple. You can be falling in orbit around the Earth, and as long as your spaceship, you know, you can't see what's going on, you would experience physics exactly the same as if you were far out in empty space. And what's probably most counterintuitive is that it's the same if for the, you know, 1 or 2 seconds you're in a broken elevator in free fall before it hits the bottom. And what he does with this is then say, okay, well, free fall looks the same, so sitting on Earth with gravity is exactly the same as if I was in empty space in an elevator or a spaceship that was being accelerated. It explains why things fall to the ground. The apple is just sitting there floating. The spaceship is accelerating. It's pushing me up because I'm standing on it, but it's not doing anything to the apple, so the apple looks like it's falling to the bottom of the elevator or spacecraft. And so this naturally explains why all objects fall at the same rate. They're just sitting there. The floor of the spaceship is coming towards them. Of course, it's going to fall at the same rate. But it also predicts that light will appear to fall. The light's just zipping along in a straight line, as light likes to do, and your spaceship is accelerating upwards, so you will see it looking like it's bending. So Einstein puts this theory together. Unlike special relativity, it is extremely mathematically complicated. But it came up with a few initial predictions. One, it explained the weird behavior of Mercury's orbit. So this was a nice initial thing to lead with. You had this odd behavior of Mercury's orbit, that the elliptical orbit turned a little bit faster than you expected it to. I think it's 2 arcseconds per century faster. So an arcsecond is 1/3600th of a degree. So 1,000th of a degree a century, Mercury's orbit is turning. And 1, that was observable, and 2, Einstein's theory was able to explain that. And it also predicted this bending of light, which was observed in a solar eclipse in 1919 and has been observed many, many times since then. And this is one of the more recent observations where you see bending of light. This purple blob is gas that's glowing in X-rays, and you're seeing the light bending around it, and it just happens to look like a smiley face. And he made a couple of other predictions. Black holes, that you could, the mathematics leads you to the idea that they're places where the whole thing just breaks down and you get infinite mass, or mass infinitely compressed. The expansion of space, that space is distances between everything should be getting bigger. And gravitational radiation, in which kind of is the analog to jiggle electromagnetic charges, and you get electromagnetic waves, jiggle masses asymmetrically, and you get gravitational waves. But he concluded that there was no way you would ever be able to measure that. And in a slide that I stole shamelessly from a talk by Ray Weiss, what Ray Weiss did was calculate, well, if you were Einstein and you wanted to calculate what you might detect in 1916, what would you look at? And you'd look at things on Earth, maybe a violent train collision, or an astronomical system, maybe a very close binary system of 2 stars. Would they be producing enough radiation? The terrestrial one, not even close. You're looking at strains of 10 to the minus 42, and I mean, the Ligo detector is talking about strains a billion times bigger than that. The astronomical system is a little closer to what scientists are looking for now, but still lower than the detector limits now. And you could think that, well, maybe you could see these stars spiraling together, but it would take 100 trillion years. So, you know, that's not really something that you can think that you'll go out and look at. So I will end before the break with the universe as seen in 1920. This is actually a drawing of the Milky Way that was made somewhat later than that. But you could see lots of stars in the Milky Way. There were these fuzzy objects that were still called nebulae. And there's lots of things in a band that has been identified as the Milky Way. Not so much stuff outside it, but lots of these fuzzy things. And that was what was understood about the universe when Einstein developed his theory. And as we'll see in the second half of the talk, things changed fairly quickly after that, both on the theoretical level and on the observational level. But this was the type of universe that Einstein was looking at when he developed the theory of relativity that we're now verifying with gravitational waves. So, questions before we break? I realized that was kind of a mad dash.
Good morning. Thank you. My name is Bob. My question really has to do with what we have learned thus far about the composition of the universe in terms of black holes. Has this study yet changed our assumptions concerning the number of black holes to be found?
I don't think you could say that it's changed it yet. I think there are hints that it might. I mean, certainly these are bigger black holes than anybody was willing to confidently assert existed before that. We don't know a lot about massive stars. And one of the things that's just been sort of burbling in the last few months is that maybe the idea that black holes make up more of the unseen matter in the universe is more plausible than people would have argued it was 2 or 3 years ago. But you know, it's 3 detections of black holes, so you know, small numbers can mislead you in unfortunate ways.
My name is Bill. The 3 solar masses of energy that was generated from loss of mass, was that mass regular matter, or was that mass regular matter and dark matter?
The working assumption, I think, would be that it was regular matter, that these black holes were stars that had collapsed. Whether it's going to turn out that to make black holes this big, you need to incorporate dark matter in some way that we don't yet understand, I think that's an open question still.
Okay, thank you very much. Let's take 10 minutes.
I'll pick you next.
This was the universe as it looked in 1920, and it very quickly became bigger and weirder. First on the observational front. So in 1923, people managed to measure the distance to what up until then had been known as the Andromeda Nebula, and it suddenly turned into the Andromeda Galaxy. And it was realized that it was a few million light years from Earth, or from the Milky Way, and looked pretty much just like the Milky Way, except far away. And that in fact, a large number of these fuzzy blobs that people had been seeing through a telescope and wondering what they were, not all of them, but a large number of them, were similar in terms of this. That they were island universes, as some theorists had liked to talk about them before then, but now you had confirmation. So suddenly the universe itself got much, much bigger. That instead of thinking about the Milky Way as kind of the extent of the universe, you have vast regions of empty space and galaxies dotted in them. And it's kind of the picture that most of us have now, but 100 years ago, people did not see the universe this way. And then very quickly after that, It was realized that not only was it a universe full of galaxies, it was a universe full of galaxies that were rushing away from each other. And this is because spectroscopy, being able to, spectroscopy, the looking at the spectral lines, the places where objects either emit at a very narrow line or absorb at a very narrow line, can tell you a lot about speeds of objects and what you were seeing. It was fairly easy to tell that galaxies were moving away from us. It in fact had been known even before their distances were measured that a lot of these nebulae were moving away from us. But now you had ways of measuring distances, and you saw this pattern that fit very nicely with Einstein's picture of expanding space, where nearby galaxies were moving only slowly away from us, distant galaxies are moving more rapidly away from us. And so all of a sudden you have this aspect of Einstein's theory that people had mostly dismissed as kind of a mathematical quirk, looking like it was actually something really meaningful. And it also leads you to the conclusion that if everything is rushing away from each other, if the universe is expanding, it was once a lot smaller, and that at some point you could kind of bring this back down to, you know, a point, and that there was a beginning time to the universe, which is something that up until that point people hadn't really thought was a sensible thing to think about. And it took probably 50 or 60 years for most astronomers to be really convinced that it was a sensible thing to think about. So now when I teach introductory astronomy, I talk about, well, the time since the beginning of the universe, and I don't expect people to bat much of an eye. And but you know, 50 years ago, it was an odd concept that a lot of astronomers held out against. Then, in terms of what we can see, radio waves were detected from the Milky Way in 1932. In one of the themes of the next 10 minutes or so, this was a serendipitous discovery. This was an antenna at Bell Labs. He was testing a communications antenna, and there were some parts of the sky that seemed noisier than the other. And he looked at it for a while, and somebody pointed out that, well, you know, maybe we should see what's out there in the sky that might be doing this. And it lined up very nicely with the band of the Milky Way in the sky. So what you discover is that not only is the Milky Way producing lots of light that we can see, it's producing lots of radio waves that we can detect with a radio telescope. And radio astronomy didn't really get going until after the Second World War. A lot of the technology for it was developed in radar communications, but it was a vastly new window on what the universe was doing. That there are sources that are really bright radio sources that produce very little optical light, and we'll run into them shortly. So around the same time, some advances in stellar evolution. Chandrasekhar calculated that there was a maximum white mass that what was known as a white dwarf star could have, and that after that, electrical and atomic forces that were known then couldn't support it, and that it should collapse. At that point, it was thought possibly into a black hole, and people who thought that, again, black holes, like expanding space, were just this weird quirk of Einstein's math that wasn't really real, found this an unsettling thought. The neutron was discovered. This is in a atomic physics experiment, the first atom smashers. That was in 1932. Astronomical theorists are a fast-moving bunch, and in 1934, a couple of astronomers, Bod and Zwicky, considering mechanisms for supernova explosions, sort of what would happen when a star got so massive that it couldn't support itself, predicted the existence of neutron stars. Basically, the idea was that they would collapse down until they were nothing but neutrons. It helped answer, well, what would happen to a white dwarf when it collapsed? It could become a neutron star. Basically, all the electrons in the material meld with all the protons in the material to form a neutron, and you get a star that's like one big atomic nucleus with the mass of a star. So they're pretty, weird concepts. And they also figured out that, well, if these things existed, they might be hot, but even if they were hot, they would be so small that they'd be about 1,000 times fainter than any known star. So kind of, interesting to theorize about, but not something that the observers were going to rush out and look for. And then we're going to fast forward a little bit to 1963, when Martin Schmidt discovered quasars. So this was after the first sort of round of radio astronomy, that in the 50s and early 60s, particularly a group at Cambridge, but other places as well, had been doing radio surveys of the sky where you're just looking for bright radio sources, for places in the sky where you're getting more radio signals than other places. And these surveys weren't very precise. You looked at with a simple radio telescope, you see very fuzzy patches of the sky, so there'd just be these big fuzzy patches where there was a strong radio signal, and some of them you could identify with objects. Jupiter is a strong radio source, so you could look at that and kind of follow that it matched to Jupiter. Some of them seemed to be aligned with galaxies, but an awful lot of them were just sources that you couldn't really see anything that they corresponded to in terms of what you could see in visible light. And so Martin Schmidt was looking at these sources, looking for them, found a sort of star-like object, so that wasn't really what people expected. You were kind of thinking, well, maybe it would be a galaxy, something big. And, people thought they understood stars fairly well, and most stars don't emit any significant amount of radio radiation. And the key insight came when he looked at the spectrum of this star. These were at that point quasi-stellar objects, and discovered that it was extremely it was moving away from us in this expansion of the universe sense very quickly. So it was extremely far away. So you had this odd source that looked like a star optically, except instead of being, it's a fairly faint star, if you thought of it as a star, instead of being in our galaxy, it's billions of light years away, or at least millions. So, very, very distant. At that point, the furthest object that had been detected in the universe. And this odd-looking stellar source and a strong radio source. And all of a sudden, there's this entirely new class of objects. Something that people really didn't know what they were. The only thing that was really clear about them was that they were producing an enormous amount of energy. So people then, now you have a target for what you can go out and look for. And one of the things that was discovered when people honed in on this object and other objects was that because of the limited radio view, they looked like out of focus fuzzy blobs on the sky. In fact, they could be localized very well, and that they were small enough that they twinkled in kind of the what astronomers call the interstellar medium. That just they were small enough that the ways that the stuff that's between us and them passed through the light waves made them twinkle in a way that wasn't washed out. That will come in again about 2 slides from now. But the other thing that was going on at around this time was one of the predictions that went with the idea that the universe was expanding was verified, and that was the idea that if the universe was expanding, it was once smaller, it was once hotter, it was once denser, and there had been predictions that if the universe was once hot and dense, there should be radiation left over from that that would have been stretched out by the expansion of space, and that it should be detectable. It was found by Penzias and Wilson again at Bell Labs, again a serendipitous discovery. From us Princeton loyalists, it was a slightly sad serendipitous discovery. There was a group at Princeton that was actually going out and looking for this radiation with a much smaller instrument. And so the group at Bell Labs finds the signal they can't explain, starts asking around, does anybody have ideas? And somebody said, well, you should call up the group at Princeton. I think they've been looking for something like this. And they were very disappointed to get that phone call. And the idea here, and this comes back to the idea of what we can and can't see with electromagnetic radiation, is that there was once a time when the universe was hot and dense and kind of like the interior of a star. That the whole universe was like being in the inside of the sun. And material hasn't coalesced into atoms yet. You have nuclei, you have electrons, and in that sort of environment, light doesn't travel very far. A photon runs into another charged particle, bounces around, and it's just scattered all over the place. And that's why we can't see the interior of the sun. We see the surface of the sun because light comes to us directly from the surface of the sun, and nothing happens to it between us and the sun in that 93 million miles that it travels. We can't see inside the sun because none of the photons that are being produced in the interior of the sun get to us unimpeded until they reach the surface, and then they can fly free. So what we see is the point where they basically are released to fly through empty space, called in the jargon the surface of last scattering. And the picture is that exactly the same thing is happening in the early universe, except that what's releasing the photons is not kind of an edge of the sun, but the fact that as the universe expands, it cools. So as the universe expands, it cools. The electrons and the nuclei form atoms, mostly hydrogen and helium. Once you've formed atoms, the light doesn't interact with them nearly as strongly as when they're separated charged particles. So we have photons. The photons that we see when we observe this cosmic background radiation have been traveling to us ever since they were kind of let go from this cosmic soup some 12-point-something billion years ago. So what this provides is what astronomers like to think of as a baby picture of the universe. It's been getting better. The first nearly 30 years of observing the cosmic background, it was really boring. Basically, it looked about the same strength in every direction. This was not terribly surprising, but there got to be a point where the measurements were getting better and better, and people had pictures of what the early universe should be looking like, and kind of it should be hotter in some places than others, a little more mass here, things beginning to coalesce a little differently, and that should show up in the amount of radiation that you're getting. And a lot of this work was being done at Princeton when I was in grad school, and it was like every time we'd come back from an observing run, we'd kind of hear what the cosmic background group was, and they'd gotten a new, better measurement that still didn't see any variations, and probably had knocked out a couple of theories of the early universe in the process, but it was getting a little frustrating. In 1992, the COBE satellite was launched, and getting above the Earth's atmosphere allowed a clearer view. You didn't have to do nearly as many corrections to what was going on in the radio waves you were receiving, and you began to see a certain amount of structure. And about 10 years later, another satellite, the microwave anisotropy probe, got a much more detailed picture. You can still see the same basic patterns that the COBE saw 10 years earlier, but now a much finer grained picture of what's going on in the universe. And what that's telling you is that there are patches of the early universe that were hotter and patches that were cooler. And that this may tell you something about what's going on in this fireball of the early universe. But what is a little frustrating about this is that this picture, the ones that I just showed, you can get a more fine-grained picture of that. But this early baby picture of the universe, and the estimates are it's sort of about 300,000 years after the Big Bang, that's the earliest baby picture you're ever going to get in electromagnetic radiation. Because, you know, just like you're not going to be able to see inside the sun because the photons from inside the sun don't get to you directly, the photons from the early universe aren't going to get to us directly. That they are being scattered, and don't fly free of scattering material until the universe is cooled down at about 300,000 years. So, you know, what we're seeing are photons that have been traveling from a place that is now about nearly 12.5 billion light years away from us, and have been traveling to us for 12.5 billion years, pretty much unmessed up by any material between us and them. And that's what we're seeing. But ones further away, just, you know, there is no way that they are going to get to us. Ones from an earlier time in the universe aren't going to get to us. So this is kind of the wall at which we can no longer, with electromagnetic radiation, see back into the early universe. So the whole idea that pushes a lot of astronomical observing, that the further away you can see, the further back in time you can look. And, you know, we're now building bigger telescopes that can see the first stages of galaxy formation in the far reaches of the universe. We're never going to be able to get past this wall of when the universe was basically ionized material. So that's kind of one of the limits of what we're ever going to be able to do with electromagnetic radiation to keep in mind. Then being kind of chronological in this, we'll go back to the idea of quasars, but actually another serendipitous discovery. There was a group in Cambridge that set out to build a telescope that would be particularly good at identifying these twinkling quasars. This is a radio telescope built with wooden posts and wire in a field in Cambridge. So kind of very different from the high tech of LIGO. And they were looking for quasars. They found some. But Jocelyn Bell also noticed that there were some signals that she was seeing that didn't really look like the quasar signals. That quasar signals are kind of random twinkly things, and these were much more regular, and kind of poked at the data a bit more, sped up the chart recorder. This is back in the days where you got all your data on chart recorders that were, you know, the pen and wiggling up and down and the And it was very quickly realized that what these were the neutron stars that had been predicted, 60 years, 30 years before, in the early 30s. So the model is that they're a neutron star, they're highly magnetized, and they radiate, they accelerate charged particles in their environment, and because they're so highly magnetized, they come in a lighthouse-like beam. The key for making this connection was that a pulsar was discovered in the Crab supernova remnant. So, they've been predicted to be formed in supernova explosions. Here you find one that is in the middle of a supernova remnant. You can actually watch this pulsar slow down slowly and figure out kind of when it was, probably first formed, and it matches pretty nicely with the 1,000-year-old age for the Crab supernova remnant, which we know was formed in about I think it's 1054, 1064. In the 1000 ADs, because the Chinese saw it. They had a pretty accurate recording of this exploding star in the sky that is in exactly the right place for the Crab supernova remnant, and now we have a pulsar that appears to be about 1,000 years old in it. So this is a slow motion view of it flashing on and off. This one is also an optical pulsar. So now you had, you're getting towards the weird kind of objects that you would need to look for gravitational radiation. So there are two things that make pulsars particularly useful for studying relativity. One is that they're extremely massive and extremely dense. So you're taking something that's about the mass of the sun, actually about 1.5 times the mass of the sun, and you're compressing it into a 10-kilometer radius or so. So you're taking it and kind of, squeezing it so that it would fit comfortably between here and Portland. So you get very intense gravitational fields, and the pulses provide extremely good clocks. The Crab actually isn't a great clock, but many pulsars are, in fact, keep time competitively with the best atomic clocks that can be built on Earth. So, this is giving people an idea that there are interesting sources that might be able to look at Einstein's theory in a way that's very different from anything that we'd been able to do before. And about 7 years later, a wonderful system was discovered. In some ways, as with the gravitational wave, the first gravitational wave detection, of the binary pulsars that have been discovered since this one, there are a few that are competitive with it in terms of how good it is for looking at gravitational radiation and general relativistic effects. But it was a long time after this one before another one that was competitive came along. So there was a certain luck in this. Basically, people started looking for pulsars. They were fairly easy to pull out of radio noise, and the survey that that found this one, one of the things they put in the observing proposal was that, it would be really cool to find a binary pulsar because, if you found a pulsar in a binary system, and since they're formed from stars, most stars are in binary systems, some of them should be in binary systems, it would be a really great thing for testing relativity. And they found one. And what you have is this really good clock. You can measure, because of the Doppler shifts, the speed at which it's moving back and forth. You can tell pretty quickly that it's moving in a slightly less than 8-hour orbit, because you can see the pulses come a little faster and then a little slower as it moves towards us and away from us every 8 hours or so. Very clearly something interesting is going on. You can work out the orbit. It's an elliptical orbit. It's much more elliptical than anything in the solar system. And so, Mercury had this precession effect due to general relativity at small fractions of a degree per century. This system, you can see that effect at 4 degrees per year. So basically, the shape of this curve tells you where the closest approach to the shape of the orbit and what time it's approaching the star, its companion, most quickly, because that's when it's moving fastest, and that's something that dates back to Kepler. And you can watch how that changes. A graph would look different a couple of years later. So they figure out that you can figure out the masses of the two stars, both the one you can see and the one you can't see, and they're about 1.5 times the mass of the sun. It became fairly clear, you have this unseen companion, people go out and look for it, you can't see it, that it's almost certainly also a neutron star. So now you have this really simple, clean system for doing general relativistic calculations. 2 nice point masses, very strong gravitational fields, and people start doing tests of, predicting how this system should behave, how it should emit gravitational radiation, and it is in fact very well behaved. So you have the 2 stars, both emitting gravitational radiation. Because they're emitting energy, so the energy comes from somewhere, it comes from the orbit of the system, they sort of fall together, releasing energy, and so it's spiraling together, and you could predict how that radiation is going to affect the orbit. So the points on this are the data points, and the line is not a fit to the curve, it's the prediction of general relativity. So you have a system that is behaving exactly the way general relativity says it should, and one of the predictions that's incorporated in this is that these stars are radiating gravitational waves. So you're not detecting the gravitational waves directly, but you're detecting the effect that the loss of energy due to gravitational radiation has on the system. So this was important for gravitational wave detection for 2 reasons. One is it confirms the idea that things do radiate gravitational waves. The other was the time scale of this, which is that these 2 neutron stars should collide with each other in about 300 million years. And on an astronomical time scale, 300 million years is like peanuts. The sun will live many times that long. So what this is saying is, here are objects that look like they could be produced in fairly ordinary binary systems and that behave in a way that suggests that, they'll live for a few 100 million years and then collide. And if that's true, we should have things that aren't just producing this kind of slow, low-level gravitational radiation, but as they get closer, they will be emitting more and more gravitational radiation, more and more strongly, and at least in the last few minutes to hours, it should be strong enough to detect on Earth. So you had both a confirmation that gravitational waves were emitted by these objects, and something that's telling you that you should have detectable sources that can be detected on Earth, going off relatively frequently on an astronomical sense, which is what got one of the things that really kind of prompted the idea that this was something that it was worth building instruments that you could go out and actually directly detect this radiation. And then meanwhile, there were also advances in coming to believe that black holes were real, that as people got better at looking at binary systems, and these come from X-ray observations. This is a star, Cygnus X1, that looks like a fairly normal star optically, but it's also producing a lot of X-ray radiation that you can't really explain. And the easiest explanation was that it was material falling onto some neutron star. At least that was the first explanation, that you couldn't see. And then people started working out the orbit and coming up with a mass of the neutron star of like 10 solar masses, and that's way bigger than anybody believes that a neutron star could be. So you have something that's looking really like a black hole. Also more evidence for them in the centers of galaxies. These ones would be millions of solar masses. This is an experiment being done by a group at UCLA, looking at stars orbiting the galactic center, and again taking Kepler's laws and looking at the orbit, trying to figure out how massive the object that they're orbiting is, and coming up with millions of solar masses in an incredibly small area that's kind of pushing it in towards this has got to be a black hole. But the problem for black holes is that by definition they emit no light. So you are never going to be able to see black holes directly in electromagnetic radiation. You can see material falling into them. You can kind of infer that they've got to be there because they're massive and dense and you can't see them, and what else could be this massive and this dense and you can't see them, but you're never going to get electromagnetic radiation directly from a black hole. So, you know, one of the kind of changes over the time I've been watching binary systems particularly is, you know, 20, 30 years ago, people talked about black hole candidates. Nobody ever said that something was a black hole. Now people are more willing to say, you know, that's a black hole binary system. But still, you know, there's this, all you can do is say, well, what else could it be? It's got to be a black hole because it couldn't be anything else plausible, which is a little unsatisfying. So this is one of the other reasons that detecting gravitational waves is interesting, because those are something that the black holes really do emit in their, you know, as they're falling together and coalescing, as they're kind of merging. That, you know, that is a system that is sending out waves that we can see, and that nothing else would be able to do it in exactly the same way. So now we get to the idea that we're really going to be doing gravitational wave astronomy, so that it isn't just detecting the waves, it's, you know, what can you tease out about what's going on in these situations that you can't probe with electromagnetic radiation. So the types of detectors and observatories we have now, Ligo and the similar detectors being built in Chile and Italy and India, are basically looking for the binary systems, the black hole binaries, the neutron star binaries, seeing the objects collapse, possibly seeing supernova explosions. Pictures of pulsars with mountains might produce them, but you're looking for these very fast explosions of gravitational waves that will last, you know, a few seconds or so and produce waves that will jiggle your detectors on fractions of a second time scales. There are other things that you would like to look at, the supermassive black holes in galaxies that are much slower, and we can't look for those yet, but it's fairly clear how we would do that. And then, in some ways, what I think many people would think were the most interesting things are the early universe, where, you know, it's still less clear technically how you do that, but the more we learn about what's going on in the systems that you can detect with Earth-based arrays or detectors, the easier it will be to imagine, you know, what you could do to detect the more complicated. So this is just sort of another view of that. This is where we are. This is the LIGO, advanced LIGO. These are the types of sources that it's going to see. The neutron star and black hole binaries. Seeing type 1a supernova would be a very interesting thing, because they're one of the ways we have of measuring distances to galaxies, and getting another way of looking at those that was completely independent would be very interesting. So that's one of the reasons to push out to longer timescales. So LIGO has detected 3 events so far, rumors of a 4th. They've all been these black hole mergers. They've all appear to be far outside our galaxy. All of them pretty hefty systems, and I'll actually, the person who does stellar evolution and binaries. In me, always go to the masses of the stars. So you're looking at the first one, 2 really hefty black holes. The second one, which was in December of 2015, somewhat smaller. These are kind of more normal-sized stars, 10 to 20 solar masses with a 5 to 10 solar mass companion. The most recent one in January of this year, again, getting bigger again. So one of the things that's interesting about this from an astronomical point of view is just that black holes this big exist. Because the end of the stellar mass spectrum is the high mass end is something we don't understand very well because there aren't many high mass stars. They don't live a very long time. They're messy things. It's very difficult to figure out really how massive a massive star is. So, people have been talking about several solar mass, 10 solar mass, 20 solar mass black holes, but it hasn't been clear quite how you form them and how many of them you'll form. So the fact that, in the space of 2-ish years, you've seen 3 of these events, all with hefty systems. I mean, as the question about how many of them there were, in the next few years, there will be some good statistics on how common these systems are, what type of stars produce them, can they be produced by the types of stars that we see in our galaxy, or are they some earlier stage of star formation or something that goes with different types of galaxies than our own. And just how, there are these numbers. How did somebody come up with them? One of the pieces of making these work as observatories was the theoretical calculation that goes into being able to figure out what a signal that you see corresponds to. And what they do, because this is not something that you can do kind of in real-time signal processing, because gravitational general relativity calculations are long and difficult and require incredible amounts of supercomputer time, is that people build models of a bunch of different types of systems and look at what types of gravitational wave signals they should produce at the detector, and then when you get something that looks like a signal, you just kind of go through and match it up and say, okay, well, this one matches with 60 solar masses and divided, 35, 25, and we know how much energy that should produce, so by the strength of the signal when it reaches Earth, we get a distance. And so that's how you tease out the astronomical information from the signal. The jargon word for them is templates. And the real hard part of them is that the last few seconds of the calculation needs to be done with lots of supercomputer time. So you kind of have to have a bank of these to throw at the data you collect rather than trying to fit your data to something in real time. The other thing you can do with this is figure out where they are in the sky, not very accurately at the moment, but a little bit. So they can only be localized to kind of swaths of the sky. It's even bigger and fuzzier than the radio view in the early days of radio astronomy. And the way you do that is by having the 2 detectors. So the signal, the wave is coming in from that, a few billion light years off in that direction. It will reach this detector, if it's from this direction, slightly before it reaches that detector, and you can use that time difference to get this angle, and you can work out basically a ring of the sky in which the signal could have that time delay. So there are really 2 reasons that you want to have at least 2 detectors. One is that signals are much more believable if you see them in 2 detectors 3,000 miles apart. Yeah, it's not an earthquake, it's not a truck, it's not some random electronics glitch. If you're seeing the same signal in Louisiana as you're seeing in Washington, it's likely to be something that's actually real and coming from outside the Earth, not something locally produced. But the other is that the more different detections you can get with these time delays, the more localized you can get it. So each additional detector on Earth is going to shrink those regions of the sky significantly. So what else is there out there besides these detectors? I mean, you know, we'd like to be able to not just see, I mean, I love inspiring neutron stars, but I realize there is more to life than that. So, you know, how are we going to look at the other parts of the spectrum? One of the ideas, and then this is also being a pulsar astronomer, close to my heart, the very long frequency ones, the idea is to use pulsars as very distant clocks, and what you're hoping to see is as a gravitational wave passes Earth, you're seeing the Earth's clocks deviate from clocks in distant pulsars that might, where the wave would have passed at different times at least, so that you're building this, you're putting clocks out there, and the waves, even from distant galaxies, which may eventually hit all your pulsars you're looking at, if they're going to reach them at different times, and you're going to see, it's kind of like looking at the Hanford and the Livingston detector, you're going to see the effects of the wave having the same type of signal, but at different times in the Earth and in all the distant pulsars. And that's still, there are groups working on that. I think it's going to be a hard thing to get convincing numbers out, at least for a while. But the pulsar group in Australia has been piling up the millisecond pulsars, which are very good clocks, at a great rate, and beginning to kind of think about how you could look at these over years of data and figure out whether, you know, in this month you can correlate a little deviation with a different deviation in another month in another pulsar. So that's the very low frequency end. Hopefully it will start telling us something about at least the overall noise level of gravitational radiation from the early universe, you know, in the next few years. The next big technical step is LISA, which is the idea of, you know, you want really long interferometers, you put them in space. You can have, you know, hundreds of thousands of kilometers, not just 4 kilometers. And the idea is to fly 3 spacecraft, put them at the Earth-Sun Lagrange point, or put one of them. You shine lasers through space. You know, you kind of think of space as, you know, well, that would be awfully wobbly, but actually space is pretty quiet. Shine lasers back and forth, and you get, it's the same concept, but you've expanded it by factors of thousands. So 3 spacecraft. And this is a project mainly by the European Space Agency. The US was involved for a while, it pulled out, and apparently is now trying to get back in again. They launched a prototype of it to kind of see what type of stability you could get, and they got even better stability than they hoped for. This was kind of the original design. This was kind of what they were really hoping for, and this was the level of stability that they actually detected. So they're all pretty happy about that. So that's, I think, going to be launched early next decade. So that will be the next big sort of, I think, producer of big press releases on gravitational wave detection. And hopefully seeing sources very different than and more exotic, the million solar mass black hole events, rather than just the common or garden stellar mass black hole events. But the thought I will leave you with, because it's kind of the big why this is interesting question, is that the universe, our current assessment of the universe, is that only less than 5% of it is made up of material that we really understand what it is, the kind of atoms that we think of as matter. There's dark matter, which appears to act kind of gravitationally like ordinary matter, but we can't see it. And that's one of the things that maybe gravitational radiation can, you know, it's not producing electromagnetic radiation. Gravitational radiation is a whole new way of probing things that don't produce magnetic radiation. And there appears to be a lot of it in the universe, and we have no idea what it is. Some theories about what it isn't, but and then there's dark energy, which is a relatively recent, it's like in the last 15 years, kind of understanding it. It appears that to understand how space is behaving expansion-wise, there has to be energy out there that is accelerating the expansion. There are various particle physicists who think they know what it is, but that's not yet clear. So that's a whole nother area where how this, you know, we can't probe it with electromagnetic radiation directly, but maybe there are things that gravitational radiation can tell us. So that's where I will leave you. And I didn't quite leave as much time for questions, but I can stay for a little while.
There are tons of hands. I think we need to lock the doors because we've got so many questions. We have exactly 2 minutes now. So I had a forest of hands. Where was the first one?
The question I have, well, I was curious that with your experiments you picked a 4-kilometer long arm each way. Why not 2 or 6 or 10 or whatever? And that leads to my main question of, would there be any advantageous situation where you set this up on the moon's surface?
So the kind of the first stage was building it with one. The push for going longer is just that you have this fractional stretching, so the longer it is, the better, basically. So that pushes you towards long, and then the technological challenges of building longer kind of push you in the other direction. So the first stage was 1 kilometer. This is 4 kilometers, and then, you know, if this produces the next stage, maybe 6 or 8 kilometers, but you know, it's a money versus detection threshold balance, and 4 kilometers was what the group 30 years ago, well, 20 years ago, pitched to the NSF. In terms of on the moon, it's not clear that doing it on the moon is really better than just doing it in space. I mean, if there were a lunar base and if we were going to the moon regularly, it would probably be worth doing, because building a vacuum on the moon is going to be a lot easier than building a vacuum on Earth. But empty space works as well, at least in the evidence from the LISA prototype, as actually putting it somewhere would do.
Well, we've run out of time. Thank you very much.
Okay.
We need